Welcome. Today we will discuss induction motor control from variable frequency, variable voltage sources, VS sources. So, the contents of my talk are like this. First I will discuss voltage source inverter fed induction motor drive, then demerits of stepped wave inverter fed induction motor drive, then features of sinusoidal PWM, SPWM inverter, then why VSI fed induction motor should have higher leakage inductance, we will have discussion. Then we will discuss cycloconverter fed induction motor drive, then we will discuss detailed analysis of stepped wave inverter and SPWM inverter. So, voltage source inverter fed induction motor drive. So, voltage source inverter VSI gives a variable frequency supply from a DC input. Variable voltage, variable frequency DC supply from DC input. VSI can be made using self-commuted switches like power transistor, IGBT, MOSFET, GTO and IGCT, insulated gate commutator theta. So, a VSI can be operated in stepped wave mode, like a stepped wave inverter or a pulse width modulated inverter. So, VSI can be operated in 120 degree mode, which is outdated now, mostly not used, and what is used is 180 degree mode, which is also known as stepped wave mode, and other one is PWM mode, PWM inverter. Frequency of stepped wave inverter VSI is varied by varying the turn on duration of switches in the VSI. So, if T is the time period of for one cycle, then each switch is on for a duration of T by 2 and all the switches are on for duration T by 2, and by varying this T or on switches of the turn on duration of the switches, the frequency is varied. T is varied means frequency is varied. So, output voltage of stepped wave inverter is varied by varying the DC input voltage. Frequency is varied by varying the turn on duration of each switch, and the output voltage of the stepped wave inverter is varied by varying the DC input voltage. So, by obviously output input voltage varies means output voltage varies. So, if available supply for is AC, then a phase control converter is used to change from AC to variable DC, variable voltage DC, and this phase control converter output is input to the VSI, stepped wave VSI, and by varying the firing angle alpha of the front end phase control converter, the input voltage of the VSI is varied and hence output voltage also varies. And if the available supply is DC, then it is changed to a variable DC using a DC to DC chopper, and output of the chopper is fed to the stepped wave VSI, and by varying the duty ratio of the chopper, input voltage of the VSI is varied and hence output voltage is varied. And a large electrolytic capacitor, filter capacitor is connected in DC link to make the inverter operation independent of phase control converter or chopper. Capacitor also filters out harmonics in the DC link voltage. So, filter capacitor is a part to maintain the DC link voltage constant. So, this is the circuit diagram of a 3-phase voltage source inverter. So, there are switches like T1, T3, T5, T4, T6 and T2. So, switches are turned on in their numbering sequence like 1, 2, 3, 5, 6, 1 at intervals of T by 6. If one cycle time period is T, then switches are switched on at interval of T by 6. So that after 360 degree or after 1 T, the cycle repeats, and each switch conducts for a duration of T by 2. This is 180 degree mode. In 120 degree mode, each switch conducts for T by 3, but that we are not going to discuss. That has been a bit outdated. And these T1 to T6 are the switches which provide out power to the load, and across each switch there is a diode like D1, D3. These are the diodes. These are the feedback diodes or feedback diodes. So when suppose motor is a induction motor load, the load is an induction motor load, and the induction machine can operate as a generator for regenerative braking. So during the generating mode, the direction of the current can be opposite. So when the current has to flow from the load to the DC side, then these diodes, feedback diodes, carry the current in the reverse direction. While the transistor carries current in forward direction, the reverse parallel diodes are connected in the carry current in the opposite direction. They are also called body diodes. They are integrated with the switch. So this is the scheme arrangement of a voltage source inverter controlled induction motor drive with AC supply. So this is the induction motor. Fed from the 3-phase voltage source inverter. So voltage source is provided a variable DC voltage through a phase control converter, because available supply is AC. A phase control converter provides variable DC voltage to the voltage source inverter, and there is a filter capacitor C, large electrolytic filter capacitor, which removes the ripples in the output voltage of the phase control converter. So that output voltage is the input voltage to the VSI is kept constant, and also the VSI is not affected by the switchings in the phase control converter. So this is the switching during switching, whatever voltage changes will be observed by the large capacitor. So switching of the phase control converter will not affect the voltage source inverter operation. This is a scheme of voltage source inverter controlled induction motor drive with front end chopper. So this is a DC supply to the chopper. So the chopper from a fixed DC voltage provides a variable DC voltage to the VSI, and there is a filter capacitor in the DC link, so that switching in the chopper does not affect the performance in the VSI or motor. So this is the circuit arrangement when the supply is DC. So what are the demerits of stepped wave inverter for induction motor drive? Stepped wave inverter means 180 degree mode VSI. Inverter output contains large harmonics of low frequency. Low frequency harmonics have large amplitude. So because low frequency harmonics are of larger amplitude, due to that there will be each harmonic voltage will contribute to harmonic current, and due to that there will be harmonic I square R losses in the windings, and also due to harmonics there will be losses, increased core losses. So motor losses are increased, causing derating of the motor. Motor rating reduces, output reduces. Motor develops pulsating torques due to 5th harmonic, 7th, 11th and 13th harmonics, causing jerky motion at the low speed. Because of these harmonics, they have torques due to 5th, 7th harmonics and which are in opposite direction, and this causes a jerky motion at low speeds. Harmonic content in motor current increases at low speeds. Machine saturates at low speeds and gets overheated. So, for high speed operation, harmonics are not disturbing, but at low speeds harmonics play a dominant role. So, machine saturates at low speeds and gets overheated. So, machine cannot be operated at very low speed due to harmonics from a stepped wave VSI. Lowest speed obtainable is around 40% of the rated speed. Below that, it is not possible to operate. Then features of sinusoidal PWM inverter. In sinusoidal PWM inverter, a sinusoidal reference signal or modulating signal is compared with a triangular signal, carrier signal. Like you can see, this is the reference signal or modulating signal. Then a triangular carrier signal is compared with a modulating or reference signal, and pulses are generated. Because the modulating signal is sinusoidal, it is called sinusoidal PWM signal. So, frequency of the output is varied by varying the frequency of the control signal. So, output frequency is same as the frequency of the control signal. For voltage control, input voltage need not be varied as per stepped wave inverter. In this case, voltage control can be done within the PWM VSI by varying the modulation index. Output voltage can be varied. Input voltage need not be varied. Constant input DC voltage is sufficient. So, PWM inverter can be directly connected when supply is DC and through a diode rectifier when supply is AC. So, fixed DC is sufficient for PWM VSI. Harmonics are reduced, low frequency harmonics are eliminated, and losses due to harmonics are reduced, low speed operation and performance are improved. So, sinusoidal PWM inverter is much better for induction motor than stepped wave VSI. Then VSI fed induction motor should have higher leakage inductance. Why? Harmonics in motor current produce torque pulsation and derate the motor. We have discussed that harmonics in the motor current produce torque pulsation and machine rating output reduces. For a given harmonic content in motor terminal voltage, the current harmonics are reduced when motor has higher leakage inductance, because current is voltage by impedance. So, if leakage inductance is higher, and then harmonic will current amplitude will reduce. So, induction motor with larger leakage inductance when fed from a voltage source inverter has reduced derating and torque pulsations. That is why machine with larger leakage inductance is used for VSI operation. Then we will discuss cycloconverter fed induction motor drive. A cycloconverter is also used to provide variable frequency, variable voltage supply from an available AC supply for induction motor control, AC to AC conversion. So, input is constant frequency AC, output is variable voltage, variable frequency AC. But when output frequency increases, the harmonic content in the output increases substantially. At very low frequency of the very low output frequency, harmonic content is okay, all right, okay. But as the output frequency increases, harmonic content increases at a fast rate, higher rate. So, maximum output frequency is limited to 40% of source frequency, Thus maximum speed is restricted to 40% of synchronous speed at supply frequency. So high frequency cannot be achieved with cycloconverter. Since cycloconverter uses large number of thyristors, it is used for high power and low speed drives. A typical circuit diagram of a cycloconverter is shown here. Input is 3-phase AC, output is also output 3 phases are A, B and C. So 3 phase to 3 phase input to 3 phase output cycloconverter. So for each phase there is a positive group and a negative group. Positive group provides the positive output voltage and negative group provides the negative output voltage. For example, for phase A, this is positive group thyristor and this is negative group thyristor. So here positive group and negative group converters P and are 3-phase half wave converters. So 3-phase half, each 3-phase half wave converter has 3 switches and it is used for one for positive half cycle and one for negative half cycle. So that each phase requires 6 switches and 3 phases require 8 switches. To reduce the harmonic content further below, then these 3-phase half wave converters can be replaced by 6 pulse converters. So 3-phase bridge converter. So there for positive group there will be 6 switches, for negative group 6 switches. So 12 switches will be used for each phase and for 3 phases 36 switches will be used. So both this is positive group, this is positive group and this is negative group. Positive and negative group are identical, only connected in like this. So positive group both positive and negative group can be 3-phase half wave converter or 3-phase full wave bridge converter, or it can be even 12 pulse converter, 36 pulse converter. Accordingly harmonic content will reduce but number of switches will go on increasing. So but it is used for high power load. Because it is used for high power load, large number of switches means each switch will have less current rating. So it is suitable for high power load, and because output frequency is less, low speed drive, motor speed cannot be increased. Only for low speed operation it is suitable because frequency is low. So because of large number of switches, it is suitable for high power load, and for low frequency output it is suitable for low speed of the load. So high power, low speed application cycloconverters are used. Then we will go to the detailed analysis of inverters. So first we will discuss stepped wave or 180 mode VSI. So for 180 degree mode of operation of 3-phase voltage source inverter, the phase voltage waveform is a 6-step waveform as shown in this figure. So 1/3 VD, 2/3 VD, 1/3 VD, then minus 1/3 VD, minus 2/3, minus 1/3 VD. This is the waveform. And for the 6-step inverter, the line voltage waveform is a quasi square wave as shown in this figure 2. So from the waveform of the line voltage, the Fourier series is like this. Fourier series for the line voltage VAB is given by 2 into root 3 Vd by pi sin omega t plus pi by 6 plus fifth harmonic is 1 by 5, amplitude is 1 by 5, fifth of that fundamental into frequency is 5 times sin 5 omega t, phase is reverse sin 5 omega t minus pi by 6. Seventh harmonic has amplitude 1/7 of the fundamental, so 1 by 7, frequency is 7 times and phase is positive sin 1 by 7 sin 7 omega t plus pi by 6, like this. The Fourier series for the phase voltage VAN is 2 Vd by pi into sin omega t plus 1 by 5 sin 5 omega t plus 1 by 7 sin 7 omega t, like this. So as you see from the 6-step waveform, the phase voltage waveform is in the fundamental component is in the time phase without phase delay, so without any phase difference, so sin omega t is there and line voltages will be pi by 6 away. The RMS value of the fundamental phase voltage is V1, that is root 2 Vd by pi, and RMS value of the phase voltage is V, that is root 2 into Vd by 3. The harmonic content of the line and phase voltages of stepped wave VSI, it is the same, only odd harmonics of the order k equal to 6n plus or minus 1 are present, where n is an integer. So for n equal to 1, harmonics are 5th and 7th, for n equal to 2, harmonics are 11th and 13th. So like that, 6n plus or minus 1 are present. The triplet harmonics, that means multiples of 3, 6, 9, 12, 15, 18, triplet harmonics are absent. So triplet harmonics are always in phase. So triplet harmonic current circulate in the delta of the delta winding of the stator. But as triplet harmonics are absent, so there is no problem of circulating current in delta connected stator winding. So next we'll discuss pulse width modulated VSI and sinusoidal pulse width modulation VSI. So in sinusoidal PWM VSI, the modulating wave or the carrier wave is a sinusoidal wave. Like this. This is the reference wave or modulating wave, and the carrier wave so this is the carrier wave which is triangular, and this is the modulating wave or reference wave. So accordingly, switches are turned on. So the current waveform, if you want to draw, so this is one pulse. This is another pulse, and here 1, 2. So by comparing the carrier wave and the reference wave, the switching instant for the switches are obtained. So a typical output current waveform is shown in this waveform, and so this is the waveform of the line voltage, which has values plus Vd, minus Vd and 0, and the waveform line voltage waveform is like this, and the scheme of the PWM inverter can be like this. So this is the PWM inverter, feeding the 3-phase motor, and if the available supply is DC, constant DC, then it is directly connected and through a filter. So this is the filter inductor, filter capacitor, this is the DC voltage. And if the available supply is DC, AC, then a diode rectifier is used, because we require only a constant voltage DC. Then there will be a filter inductor and a filter capacitor CF, which filters the ripples and fix and feed a constant DC to PWM VSI, which feeds the 3-phase motor. This is, let us say, figure 3A. Figure 3B. Both are for scheme of PWM VSI fed induction motor drive. So some features: output frequency, of PWM VSI is the same as the frequency of reference signal, reference voltage. Then we define modulation index. Is the ratio of amplitude of the reference wave to that of carrier wave. So modulation index M is amplitude of the reference wave divided by amplitude of the carrier wave. fundamental RMS component in output voltage, output phase voltage is V1, which is M modulation index M times DC input voltage Vd divided by 2 into root 2. So as you can see, by varying the M modulation index M, the output phase voltage is varied by this expression. So amplitude of the carrier wave is generally kept constant. So modulation index M is directly proportional to the amplitude of the reference wave, and by varying, and output phase voltage is directly proportional to the modulation index, as you see in this expression. So by varying the amplitude of the reference wave, the output phase voltage is varied. So if modulation index M is less than equal to 1, so this is PWM, pulse width modulation is obtained. Pulse width modulation is obtained. So linear characteristics is obtained. Linear relationship is obtained. Linear relationship means output voltage V1 is directly proportional to modulation index M, that is linear relationship. If modulation index is greater than 1, which is called over modulation, then sinusoidal PWM is not obtained. So this linearity is lost. Then like amplitude modulation index, also the frequency modulation index is defined. Frequency ratio or frequency modulation index or frequency ratio. P, that is frequency of the carrier Fc divided by frequency of the reference. So when the frequency ratio, that is frequency of the carrier by frequency of the reference, is large, the frequency of the harmonics is large compared to the fundamental. So harmonics, so with this PWM harmonic spectrum is shifted from low frequency region to high frequency region. So low frequency harmonics are absent, so filter is not required. Higher order harmonics are present, but they can be easily filtered with the leakage inductance of the machine. So current approaches a sinusoidal waveform. In some cases, a small size filter may be used. Thank you for attention.